So I'm trying to write a paper, and I hate writing, and so I want to talk about it instead. As a way of trying to organize my thoughts and record them before trying to put it into writing. And I'm not sure exactly what John talked about in the seminar at that time, but for my purposes, it doesn't matter too much if I'm repeating ideas that you already talked about, because I'm trying to tell a relatively complete story in my own words, my own point of view, and you probably got much for talk anyway. So let's. So the working title for the paper that I'm writing is Algebraic Geometry, or category theory. And so let's see. So if I look at this audience, then the first thing that comes to my mind isn't really category theory. I'll show you the first thing is. And so I have to deal with that some way, to a mismatch between this audience I had in mind and the actual audience here. So I may end up in these lectures trying to explain some category theory background more than I was actually planning to try to write in the paper. I'm not sure exactly how many lectures I can try to give before I run out of things to say, but let me try to summarize what I'm going to say in the lectures right now in sort of slogan form, and then the rest of the lectures will more or less be trying to explain this slogan, modify it, qualify it, amplify it on it. And so let me try to write down the slogan right now. So, every space is a moduli space of models of a theory of a doctrine. I guess I'll stop there, although maybe you can keep going. Let's see. Well, that's not quite the end of the slogan yet. Every space is a moduli space of models of a theory of a doctrine. And key to understanding algebraic geometry is to identify and understand the doctrines that are involved. So there's a bunch of technical sounding words in this slogan. And the fact that they're technical sounding doesn't actually guarantee that they have a technically precise definition. But a lot of what we'll have to do we'll be explaining some of these technical sounding words, what they mean. Particularly this one here. Well, this word doctrine here, that's where a category theory background really comes in useful here, because doctrines are something that category theorists work with all the time. They might not even use that terminology all of them, but they use lots of different doctrines all the time. So, for example, there's the doctrine of operas, the doctrine of algebraic theories, the doctrine of the toposes, roughly speaking. And category theorists use all those kind of things all the time, or lots of those kind of things all the time. And so, for a category theorist, it's nice to know that the only thing you really need to really understand algebraic geometry is you need to know what are the doctrines that are involved in it. You need to know what are the doctrines, you need to understand those doctrines, and you need to understand how they're involved in algebraic geometry, which is along the lines of this slogan here, which we'll be trying to explain. So, that's my attempt to give a beforehand summary of what we're talking about. So, well, so I just talked a little bit about some sort of category theory background that I'm sort of pretending the audience has, although I'll be trying to explain it a bit. And there's also a bit of algebraic geometry background that I'm assuming or pretending the audience has. I guess one of the prerequisites for learning algebraic geometry is you should understand algebraic geometry already. Which is actually pretty difficult, I think. I mean, that's pretty easily done. But it's not quite that bad because, okay, so what do I actually mean here? So, well, let me try to say what the algebraic geometry prerequisite is for what I'm going to be talking about. So, basically, you should have taken algebraic geometry before, been exposed to it before, and you should have flunked it, basically, sort of roughly like I did. But you should have come away from that experience with at least one thing that you did learn, and that is sort of the easy part of algebraic geometry, which is affine algebraic geometry. And so that's going to be a bit of background that I'm going to require, but I'll start by trying to give some of that background right now. So here goes. I'll try to give a quick summary of affine algebraic geometry. I'm going to try and describe it at roughly 3 levels of abstraction, starting out a little bit more concrete, getting a little bit more abstract, and then still more abstract. So I'll try to list 3 levels of abstraction here. First level of abstraction is basically where you have variables, like, say, x and y, and have some equations, like, say, x squared plus y squared equals 1. and you study the solutions of this equation. And the solutions form a space of some kind. I guess a subspace of the xy plane. And so that means you're doing a kind of geometry. You're studying a space. And moreover, you're using some algebra, so it's algebraic geometry. So that's how algebraic geometry kind of starts out. And then it gets a little bit more abstract when you start thinking of the variables as generators of a polynomial ring. And you start thinking about the equations as giving you an idea. The equations generate an ideal in this polynomial ring. And the basic idea at this level of abstraction is that ideals correspond roughly to affine algebraic varieties. Affine varieties, some sort of fancy name for a space, roughly speaking. Affine algebraic varieties that live in a particular, really that live in this xy plane again. So, but we're now at this level of abstraction, where the basic idea is that the correspondence between these ideals and these affine algebraic varieties. Now, the third level of abstraction is when you take this polynomial ring and you take this ideal and you do the sensible thing, which is you mod out the polynomial ring by the ideal. So you get a quotient ring. And all the rings we deal with here are commutative rings. So you're getting a commutative ring as a result of quotienting out this polynomial ring by this ideal. And the basic idea is that that commutative ring is now kind of a thing that corresponds to an affine algebraic variety. It does it in roughly this way. It's like the ring of algebraic functions. There's say polynomial functions there or something like that. But there's a lot of things I'm being sloppy about here, so it's okay. The ring of algebraic functions on the variety. And so that's what I'm calling this third level of abstraction, where you kind of forget the original polynomial rings and the ideal in it. You just think about the quotient ring that you get when you mod that out, and you geometrically interpret that quotient ring as being the ring of algebraic functions on the variety that you're studying. And I guess this third level of abstraction is sometimes summarized by saying that we have an equivalence of categories between the category of affine schemes and the category of commutative rings, meaning opposite, meaning in the category of theoretic sense, we're turning all the arrows around. You have to think about how maps between this word scheme here, that's just yet another fancy word for space, just like variety is another fancy word for space here. So just another fancy word for space here, but it's more technically correct in this context. So the category of affine schemes is equivalent to the category to the opposite of the category of commutative rings. Because when you have maps between these spaces, it gives you a ring homomorphism, but going in the backwards direction. You can pull back algebraic functions along this algebraic map, or this geometric algebraic map, algebraic geometric map. And so that's a way of sort of summarizing what's going on here. So that's supposed to be my review of affine algebraic geometry. And So that's what strikes me as the easy part of algebraic geometry. The part that I never had any difficulty, and I think category theorists in general never had much difficulty with this way of thinking, because it's like this, a very category theoretic way of thinking.
It's a definition.
What?
It's become a definition.
Yeah. I mean, this is a perfectly lovely category, or perhaps that's a perfectly lovely category. And that's a perfectly co-lovely category. So, and it's got lots of nice properties. Category theorists love those properties. And so this is the easy part of algebraic geometry. So the hard part for me was getting past this stage where people start talking about projective varieties or these more general things, these non-affine schemes. That's pretty much the hard part. So that's the part that I'm really trying to explain. And I'll basically try to start doing that now. And I'm taking a certain approach that I think is different from what I know of as the traditional approach. It's like the traditional approach just never worked for me. I just never really understood what was going on in algebraic geometry. And so I'm going to be trying to give somewhat, I think, as far as I know, non-traditional approach. But if I just completely get a non-traditional approach, then you won't even believe that I'm doing algebraic geometry. So I can make some attempt to connect what I'm going to be talking about with the traditional approaches to algebraic geometry. So I'm going to start out giving a little bit of the traditional approach to algebraic geometry beyond the affine states. But just to kind of label the distinction between the traditional approach and the non-traditional approach, I'm going to refer to it as the lowbrow approach versus the highbrow approach. Lowbrow approach being sort of traditional approach to the algebraic geometry approach to algebraic geometry. Highbrow approach being the category theory approach. It's really just a meaningless label. Sort of self-deprecating and other-deprecating at the same time. You don't really want to be either like lowbrow or highbrow, but
Or middlebrow.
yeah.
So we want to be no brow?
Or unibrow. I don't know. So I'm going to start on the lowbrow approach. So starting on the lowbrow approach, again, it's supposed to connect with the usual lowbrow way of doing things. Before I go into the highbrow approach, they try and lose everybody. So basically the first step beyond affine algebraic geometry is projective algebraic geometry. Instead of studying affine varieties, we're going to be studying so-called projective varieties. So that's what we're going to be talking about. And with the lowbrow approach, I'm going to start out imitating this a lot. So again, I'll roughly speaking, so it won't be any fast math, but roughly speaking, I'll have these same three levels of abstraction. And there'll just be a couple of differences. And so we start out with variables and equations. But the big difference now in the projective case is that we're going to have so-called homogeneous equations. So they're still polynomial equations, just like they were over in that case. But we can't have this example anymore. This is not a homogeneous equation. Homogeneous means that all of the terms in the equation are the same total polynomial degree. This is second degree, x times x. This is second degree, y times y. This is 0th degree, so it's different degrees from the other terms. So it's non-homogeneous. This is 0 degree because there are no variables that are being multiplied together at all in this term over here. So this is no good. It's an example. You could, well, it's slightly convenient actually to have an extra variable. It doesn't really do much difference. This is just for an example. But I've now given the example of a homogeneous equation here. And you basically do the same thing with this equation, or it could be a system of equations. You could have more than one equation. You could have a whole system of equations here, just like you have such equations here. And you basically do the same thing with this kind of system of equations that you do with this kind of system of equations. The solutions form a space, but I guess the big difference is that you don't distinguish different solutions from each other if one solution is obtained from another just by rescaling. So you could have like if you have some solution to this equation over here, and then if you have, well, if you have a solution here, and then you take all of the coordinates of the solution, and if you multiply them all times the same scalar, you consistently rescale the solution, and it's automatically a solution of the equation again. So that's just automatically a solution of the equation. I mean, there's not really an interestingly distinct solution. You count it as the same solution. You know, there's some sort of equivalence relation on these solutions. Yes?
Is there an interesting process of algebraic spaces of you're just getting an equation, this is what we're over here, add it up with some dummy variables, homogeneous?
Yeah, I mean, it sounds like you're saying, and is there some idea here where you systematically take a non-homogeneous system and introduce an extra variable for the whole purpose?
That's something interesting.
Yeah, I mean, there are systematic processes here that will take an affine variety, which you could picture as being a somewhat incomplete thing, because it's like a non-compact thing. And then there are ways to complete that to give a projective variety. And in the traditional story, people often say that projective varieties are motivated partially because they're more complete than affine varieties. And this kind of process where you take an affine thing and you turn it into a projective thing by adding an extra variable, that's one of these completion processes. If you think about it, it has a tendency to sort of add points at infinity to your affine variety and turn it into a projective variety. Yeah, you have to think about that a bit. Just draw pictures of it and see how it works. But that's one of the things that's going on here. So that's why I found technicality here about how it's important for the scalar k here, that's rescaling the solution. It's probably important for it to be invertible or something like that, but I'm not going to worry about that in a quick moment. So, well, okay, but I said that you count solutions as equivalent if you're rescaling them. What we should say, we should try to say a little bit more intuitively, geometrically, pictorially, what that means in terms of why these are called projective varieties. So it's because these are living in so-called projective space. I mean, I guess this is, points like this are points of the projective plane. You have 3 coordinates, but this extra variable z is just being used kind of for completing beautifying purposes. It's really geometrically a plane, a 2-dimensional thing, just like it was over here. And this is one way that it sort of coordinatize the projective plane, but with an extra coordinate. And to compensate for the extra coordinate, you have to mod out by this equivalence relation. And this describes the so-called projective plane. Again, in technicality, you have to don't fill out all of these 0. That's not a fixable point. It's more objective. plane. Yep.
It's not exactly the plane, it's some 1 point percent case of the plane. Because that's where you're creating the point.
I said the projected plane. So there's an original flat affine plane.
Right. Okay, but that's fine.
But now I'm talking about the projected plane,
Right.
which is still called a plane.
Yes.
Yeah, okay. I mean, but it's descending from the affine plane by having this point independent. But then an even further annoying point, which we probably at this point want to exclude it completely. We have all zeros here. That's not an official point of the projected plane. Okay. So that's the first level of abstraction. And maybe I should say over on this side, I should say the solutions form a subspace of affine space. And on this side, I should say the solutions form a subspace of projective space. At the second level of abstraction, we still got the variables that are, again, generators of a polynomial ring. The equations, again, they still generate an ideal. But because the equations are homogeneous, they generate a special kind of ideal, which I guess is called the graded ideal. This notion of graded is related to this idea of homogeneous. Homogeneous is about things being all the same degree. And grade and degree are kind of synonyms. And a graded ring is a polynomial ring is an example of a graded ring. You can separate all polynomials into terms of different degree. And it's called a graded ring. And the ideal that you're getting, because it's generated by these homogeneous equations, the ideal sort of respects the grading. And it's called a graded ideal. And so we have a similar sort of correspondence, roughly speaking, that now we have graded ideal is the thing that corresponds to a projective algebraic variety. And so that's that kind of second level of abstraction. The third level of abstraction is, once again, the original polynomial ring and the ideal. They sort of lose their individuality, they lose their separate importance. You then consider the quotient ring. And because the ideal is a graded ideal, and the original polynomial ring was a graded polynomial ring, when you mod out and you take the quotient ring is now a graded ring. So you're getting a graded ring down here, a graded commutative ring. And roughly speaking, this is now the thing that corresponds to the projective algebraic variety, the graded commutative ring. So I'd like to say something sort of like this. Back in the affine case, this was sort of the geometric interpretation of the commutative ring that corresponds to the affine algebraic variety. It's the ring of algebraic functions on the variety. What kind of analogous statement can we make about the graded commutative ring that we're getting over here? How does it correspond to a projective algebraic variety? We'd like to say that this is sort of the ring of what? There's a kind of a blank that I want to fill in here. On the projective variety. And it probably should be tempting to think that it should again be something like some kind of functions. It's probably a reasonable guess that you think of this graded commutative ring as being a ring of some kind of functions on your picture, right? But that's not quite right. And you can tell, you can get a hint about why it's wrong if you think about if you try to think about this in a somewhat intuitive geometric way, and using certain facts which we learned from some other geometrically tinged areas of mathematics, such as complex analysis and complex differential geometry. I don't remember if we actually said what field we're working over here, but in algebraic geometry, it's very fluid as to what field we're working over. This could have been real numbers, which we describe as intuitively a circle, but we could also be working over the complex numbers, and in fact, sometimes, a lot of times, we're working over all fields at the same time. In that sense, it's a very fluid choice as to what the field is. So it's certainly legitimate to take what we're doing now and think of it as involving the complex numbers. Because I want to exploit certain things that we probably, well, we may have learned from complex analysis and complex differential geometry. So kind of think of what we're doing here as involving the complex numbers. And perhaps it helps to think of the case where these algebraic varieties are non-singular in some base sense. Just because that will help us to believe, maybe, that the algebraic spaces that are embedded here are actually complex manifolds, so that you can apply things you may know about complex manifolds to this situation. And what you might know from learning about complex manifolds is that on a compact complex manifold, and the projective varieties that you're getting over here, if you think about them, they end up being they're more complete than the affine varieties, and they tend to be compact. Maybe they're all compact, I don't know. And there's a shortage of globally defined nice functions on compact manifolds. I forget exactly what theorem I should be quoting here, maybe the maximum modulus theorem or something like that. But there's some sort of tendency that the only really nice holomorphic functions you can find on a compact complex manifold are like constant functions or something like that. Constant functions are not good at separating points from each other, right? And that's sort of what we want functions to do, the geometric purpose that they can sort of serve. I mean, geometry, right, is sort of like God's way of keeping everything from happening all at the same place. You need something to separate different points from each other. And constant functions don't do that very well. And over here, we have algebraic functions that separate different points from each other, and that's what's going on in this way of using a commutative ring to correspond to an algebraic variety. And it's starting to be exactly that same idea. That doesn't work in the case because of this shortage of non-constant functions. So you have to kind of think about what these things are here. If they're not functions on your projective variety, what are they? Kind of think about it a bit. And there's probably all sorts of good conceptual, geometric, tutorial ways of trying to explain what these are, but I'm not really going to try to do that right now. I'm really just going to give the answer, really. If you think about this, what this is really sections of line bundles. That's the geometric conceptual interpretation of what the elements of this graded commutative ring are. Again, there's a question of how much do you already understand about what line bundles are, and there are probably very variable answers depending on who the audience is exactly. But let's not worry about it too much right now. I'm really getting to the point here where I'm about to switch from the lowbrow approach to projective geometry to the highbrow approach to projective geometry. And really what I'm trying to do is I'm just trying to highlight this phenomenon going on here. And then we'll use this as a clue about what's really going on in algebraic geometry. And when I say what's really going on, I mean what's the genesis of the highbrow approach to algebraic geometry. So, I mean, in some sense, maybe I should say a little bit about what sections of line bundles are like. They are some sort of weird generalization of functions. In some sense, they're the closest thing that you can get to functions in this situation where there's a shortage of genuine functions. So they're some sort of substitute for functions. And sometimes they're sort of described as twisted functions in a certain way, because line bundles are sort of twisty things in a certain way. And well, so this is the key idea that we're going to use as our starting point for our highbrow approach. The idea that sections of line bundles are important in understanding a projective variety. So, what's secretly going on here is that you're understanding a projective algebraic variety by understanding the category of line bundles over the variety. So we're now going to start over focusing on this idea. We're going to try to understand a projective algebraic variety by understanding the category of line bundles over that variety. So now it's time for that. It's time to start again with that idea. So this is now the highbrow approach.
Just a question.
Sure. Yeah.
What about the idea of homing the ring into the ground field, or the algebra into the ground field? You didn't mention that at all. And that, if I remember correctly, isn't that like another name for the affine variety?
Yeah, it's basically equivalent to what we were talking about. I was trying to give a really brief introduction to what's going on, and I didn't even make it brief enough. So, so what are you saying? You're saying that homing the commutative ring into the ground field. Well, perhaps one place where that is secretly hidden in what we were talking about was we talked about the contravariance, the backwardness of the correspondence between algebra and geometry.
Right.
So you have a homomorphism from your commutative ring into the ground field. We should geometrically interpret that by thinking of it the other way around. So you have a space that corresponds to the ground field, and that should really be a one-point space. And that should be mapping into your space. So there's probably lots of other things to say about that, but that's one way to think about it. That a homomorphism from your commutative ring into the ground field, you dualize that from algebra to geometry, and you realize what it's telling you about. It's telling you about a single point of your space, point parameterized by the spectrum, so to speak, of this field that you're homing the commutative ring into.
Okay. And is there analogous sort of construction for projective geometry? Or is that...
There is. There's a very interesting question with lots of different answers, and I won't try to answer it right now. Maybe I'll try to answer that question later, because there are definitely lots of interesting answers that are implicit in what I'm going to be talking about. Maybe I will accidentally talk about that, but I'm not going to really try to directly address that question right now.
Okay.
In the covariance you were just talking about, are you at all using covariance to the hum, or are you using different? There's the two?
Well, it's coming from the conference to versus slot.
So you're
That's
thinking-
one thing.
I got it, yeah.
Right, I mean, you're going to hum or C, and then you're thinking this puts you going a map from R to C, and then hum that map. So you want to turn that around.
I got so. I
So
mean,
you have to ring to the ground field, and then hum each of those things plus that morphism. Turn that around, and you have hum CC mapping to hum RC as in your other guy.
I think that's right, sir. That's right. Okay. So, okay. I'm going to try the hybrid approach here. I'll start with the definition. A line object in a symmetric monoidal category is an object with two properties. First of all, it should be invertible with respect to tensor product. Tensor product is what a symmetric monoidal category is kind of all about. That the tensor product is the fact that it's symmetric. So a line object is required to be invertible with respect to tensor product. And the second thing is that the self-braiding, or the self-symmetry, or whatever it's called, I'll call this line object, I'll call it L for line. A line object L should be invertible with respect to tensor product, and the self-braiding from L tensor L to L tensor L, you know, that's the symmetry of the tensor product, should be equal to the identity morphism, should be equal to 1. So, if you know anything about line bundles, and you think about what they're like and how they behave with respect to tensor product, then you should probably notice how this definition is abstracted from the case of line bundles. These are properties that line bundles have. So line bundles are going to be important examples of line objects. And I guess as this is a symmetric monoidal category, I didn't require yet that the category should be enriched over vector spaces or enriched over modules of some computer ring or something like that. I didn't require that yet. But that's the main application, that's the main context where you apply this definition. Let me give another definition. A dimensional category is a symmetric monoidal algebraic. So algebraic is some sort of fancy name not sure I really like it, but it's a fancy name for a category where the sets are something like vector spaces or modules over computer ring, or if this would be anything, something like that. Basically, when you have parallel morphisms in algebra, you should be able to add them together and subtract them, things like that. So a dimensional category is a symmetric monoidal algebra where all of the objects are line objects. So you might ask, where does this name dimensional category come from? Well, we talk about line bundles, line objects. You know what a dimension is? A dimension is kind of like a line as well. A single dimension is kind of like a line, sort of a one-dimensional spectrum along which things can vary. That's one of the reasons we call this a dimensional category. But another reason is because this is really related to something called dimensional analysis. So this started out being algebraic geometry for category theory. But it seems to be sort of morphing into algebraic geometry for category theorists who have sort of dilettantish interest in physics. Sort of like me, I guess. Because this dimensional analysis is something that shows up in physics. And dimensional categories, if you think about it, well, we'll try to see. We'll try to see how dimensional categories are really all about dimensional analysis. Dimensional analysis is all about dimensional categories. We'll try to do an example just about almost right away. That's supposed to illustrate what's going on here. How the concept of dimensional analysis, which is often introduced to like high school students, for example, who are just beginning to learn physics, because it's useful at a very elementary level in physics, sort of organizing some of the phenomena that happen in physics. So I want to give an example here. I guess before I give the example, I should sort of state a theorem, sort of the main theorem, the fundamental theorem about dimensional categories, which will sort of be useful here. And it will tie in with some of what we were talking about algebraic geometry. So let me try and state a theorem here. Actually, before I say the theorem, let me just make one comment about dimensional categories. A dimensional category is a type of category. And that's useful because the concept of category comes associated with a whole bunch of auxiliary concepts that are very useful in category theory. So there's notion of category, there's notion of functor between categories, there's notion of a natural transformation between functors. And dimensional categories, being categories, they enjoy existence of that kind of thing. So in addition to dimensional categories, it's going to turn out there are things called dimensional functors and dimensional natural transformations. And you use these things in very useful ways, very much like you use them in category theory in general. And they will help in understanding what's going on with dimensional analysis. But first we're going to try to state a theorem about dimensional categories. The theorem says that the concept of a dimensional category is equivalent to the concept of what I'll call a dimensional algebra. So I have to tell you what a dimensional algebra is. A dimensional algebra is a kind of graded commutative algebra. Remember a moment ago we were talking about graded commutative algebras? I guess we're talking about graded commutative rings. Not that much difference between rings and algebras. The dimensional algebra is what is it? I guess it's a commutative algebra together with an abelian group. A commutative algebra R together with an abelian group G and a grading of R by G. So I guess when we were talking about the Lograr approach to projective algebraic geometry, and we mentioned graded commutative algebra. And if you think about the kind of graded commutative algebra that we're talking about there, the grading group was always really just Z in that case. Or you might even have thought that it was just the natural numbers. But even if it's the natural numbers, you can still think of it as being all the integers, because you can just think of the negative integers as all those grades as being empty. So it still fits as a case of this definition. So this is what a dimensional algebra is, and I'll try to say a little bit about how the theorem works. But I'll also say that because these two things are the same, a dimensional category and a dimensional algebra, there's another name that I'll also use for these things. I'll also call them sometimes dimensional theories. And indifferently, you can think of a dimensional theory as being either a dimensional category or a dimensional algebra because of this theorem that says that these two concepts are equivalent. And it's very useful to be able to switch back and forth between these two different viewpoints whenever you feel like it, whenever one viewpoint seems more congenial to you than another viewpoint. So let me try to say how the proof of this theorem works. So if you've got a graded commutative algebra like this, how do you interpret it as one of these things, as a dimensional category? Well, you do it in this way. The objects of the dimensional category, those are equal to the grades of the dimensional algebra. And then you have to say, to describe a category, you need objects and you need morphisms. So you need to say what the morphisms are. We've already said what the objects are in this category.
It might be nice to just also say that these elements of G. But, yeah, why is C so less? So your objects form a group in the relational category?
Yes, because remember, one of the assumptions, well, one of the requirements is they're all line objects. A line object is invertible under tensor product. So tensor product is like a group operation, and it's a symmetric thing, so it's not just a group operation, it's an abelian group operation. But the fact that they're line objects are required to be invertible with respect to tensor product. So that's why it's not just a monoid, but it's actually going to end up being a group. There are various technicalities here, like about how strict is the symmetric monodal category, symmetric monodal algebraic. We don't have to worry about those technicalities right at the moment. They work out fairly nicely most of the time. So you take the objects of the dimensional category to be the grades of the corresponding dimensional algebra, and for the morphisms, you take from one particular grade to another particular grade to be equal to elements of grade G2 over G1. There's a notational choice that you can make here about what you think of the distribution group G, what you think of as being additive or multiplicative. And in a lot of contexts, it's more traditional to think of as being additive. But there's actually good reasons why it shows, instead of saying G2 minus G1 here, there's a big conjecture reason why I decided to call it G2 over G1. It has to do with this idea of dimensional analysis, which I'll try to explain in an example now.
It also sort of has to do with how you write composition of multiplication.
Yes, there's actually just a bunch of good reasons. It's going to cause confusion either way, but there's actually probably less confusion. Well, better for the mind if you think of it as division. Yeah?
Well, I feel like you're taking elements of an element.
Say it again?
I feel like you're taking elements of an element.
Yeah, that's true. I mean, this is a double level thing here. I mean, there's elements of G, which are grades of the theta ring, and there's elements of R, which are elements. You see, the ring R is organized into grades. Those grades are the elements of G.
So the elements of R of grade,
Yes.
but
Well, but I agree with you. They are elements of elements.
Yeah, so we're thinking of the group G is composing of the object and the elements, the ring of the ring elements doesn't work.
Yes. But you have to. But when you talk about morphisms, you have to think about domains and codomains, and this is the way you organize it. So I guess the point is that an element of the ring actually lives in many different contexts, because you can express a thing as a fraction in many different ways, and so it lives in all those different concepts.
But there's going to be lots of ones that won't be, just zero.
Say that again?
So there'll be a lot of these comps. So, so if I'm thinking of just an example of something that's graded by Z, there's lots of choices of G1 and G2 where there aren't going to be ring objects to take one the other except for zero.
I think you're particularly alluding to the flavor example that we were giving,
Right.
where we actually started with something that was really graded by the natural numbers, with all the negative grades being empty.
Yes.
Sometimes we'll have the negative grades being none, but in the example that we gave, I think if you check what we did, you would have all these empty or almost empty. I guess they just have a zero morphism in them or something like that. And so yeah, there's going to be a lot of Hom spaces that are going to be trivial in these examples. Some of the Hom spaces will be non-trivial, some will be trivial. That's right. And that's important, actually. I'm not saying it's about all I'm going to say about this. theorem. The proof is very nice and very easy, but I'm not going to say much more than this about it right now, unless I somehow get forced to. So I really want to try to do an example now that really talks about dimensional analysis. So let me try to do it again. So this is an example that John came up with. I guess it was very easy for him to come up with an example because there's like a physics background. And so you remember how the example works. So it's a sort of, semi-realistic physics example. We'll imagine, and we said, it's one of the reasons it's only semi-realistic is that we started out with a slightly more realistic example, and then we kind of pared it down to make it a little bit easier to see what was going on. So imagine a physics situation where you've got what? Let's say there's two particles. Not two particles. And they each have their own mass. So we have mass M1 and M2. Mass of the first particle, mass of the second particle. And now we're going to keep track of the velocities of these particles at two different times. So we're going to have, let's see, we need two different times, and we have two different particles. I guess try to keep the names organized a little bit. I'll call them the particles. I'll call them P and Q. No, that's not good. I'll call them X and Y, I guess, or A and B. So we have the mass of A and the mass of B. They're two quantities that we have, and then we also have some velocities. And we'll keep track of the velocities at two different times. So we'll have the velocity of A at the first point in time, and we'll have the velocity of A at the second point in time, and we'll have the velocity of B at the first point in time, and we'll have the velocity of B at the second point in time. So these are going to be quantities. I guess there's 6 quantities here. And these are going to generate an algebra for us. Okay? These are going to generate an algebra for us. And but then we're going to put some relations that reflect some relatively common sense physical principles, like conservation of momentum, and conservation of energy. So let's see if we can figure out how to express these ideas, conservation of momentum, conservation of energy, how to express them in terms of these quantities. So in particular, we mean conservation from one moment in time to the second moment in time. So how do you express the idea of conservation of momentum? So you need to know some basic physics definitions here. The momentum of a particle is the mass of the particle times its velocity, something like that. And then conservation of momentum means that the total momentum between all the particles is being conserved from one moment in time to the next moment in time. So let's try and write that down. What does that say? Let me tell me what it's saying.
MAVA plus MBVB all 1,
The mass of particle A times
VA at time 1,
at time 1 plus
plus the same thing for particle B.
this is the original total momentum. It's equal to the final total momentum. Okay, hopefully that's the way to say it. How do you say conservation of energy?
Put squares on the V's.
So it's pretty much like this, except that there's squares on the B.
Yeah, and usually a 1/2 is under, in front of the M.
But that 1/2 is like one of those
Exactly, you can't.
scaling constants, it doesn't really change things, so we can leave it out, I think.
That's too big.
Oh, that's a square, that's where the square goes. Sorry, I'm getting the squares here. That's conservation of momentum, and that's conservation of energy. And you should be able to check that these are homogeneous equations. This equation is purely in the momentum dimension. Has lots to do with why it's conservation of momentum.
You're using homogeneous in a new improved,
In a what?
in a new improved sense from the last time you used that.
Am I really?
You're using a grading that's even better than a
Oh,
grading.
okay, right.
Never quite.
Right. So, okay, that's true, that's right. It's like multi-homogeneous, because we're actually keeping track of the degrees, not just the total degree of the polynomial, but the degree in each variable separately. So that makes sense.
The
It's
degree of
kind
each type of variable.
Say it again?
The degree of each type of variable separately. So there's a mass type
Yeah.
and a velocity type.
Right. We have two basic physical dimensions that you would be talking about here, and one of them is the mass dimension, one of them is the velocity dimension. And then these generate an abelian group, a whole abelian group of other dimensions, like there's the momentum dimension, which is mass times velocity. And there's the energy dimension, which is mass times velocity squared. And this whole thing is in the energy dimension. This whole thing is in the momentum dimension. So yeah, so there's actually the gradient group, when you have these two basic dimensions, masses, and velocities, the whole gradient group is z squared, because it's generated by the two generators of mass and velocity. So we're getting a graded commutative algebra here. We're getting a commutative algebra generated by these quantities subject to these homogeneous relations. And because they're homogeneous in this way, the whole algebra is graded by the abelian group of the physical dimensions generated by mass and velocity. So we have a graded commutative, we have a dimensional algebra, just like it says here. And by the theorem, that means we have a dimensional category, or a dimensional theory. So the objects of this dimensional theory, the objects of this dimensional category, are these dimensions, like mass and velocity and momentum and energy. So each dimension is an object, and they're line objects. And in fact, they're like line bundles. So this is supposed to be a classic example, reasonably classic example, of the phenomenon, which we're supposed to see this phenomenon happening in several different places. The phenomenon of, the expression goes, that learning that you've been speaking prose all your life. In other words, it's some fancy thing that people talk about, and it turns out it's really some homely thing that you already know all about. And the example that we're supposed to see with that here is that if you're a physicist, or even just a dilettante physicist, or even just a high school student learning physicist, physics, who knows about dimensional analysis, and who thinks about these different dimensions like mass and velocity, and momentum and energy, and you think about different quantities that have those dimensions, then secret, what?
Teacher hits you over your hand with a ruler if you add a mass and a velocity. That's part of the learning experience.
Yeah, that's the kind of grading. You're supposed to keep things separated into different grades. Different grades are not supposed to socialize with each other. Again, there's really many examples of these prose that you suddenly realize that you're speaking. But the particular example of prose that I'm talking about here is the person who has worked with dimensional analysis, the person who has worked with dimensions and quantities that live in those dimensions. That person has really been dealing with line bundles and sections of those line bundles, which is, you might think it's a sophisticated thing, except that it's not really sophisticated at all. And that's supposed to be one of the key ideas here. That you shouldn't be scared of line bundles and sections of line bundles. One of the ways to think about what line bundles really are and sections of line bundles really are is line bundles are simply these dimensions that show up in dimensional analysis. And the sections of the line bundles are the quantities that live in those dimensions. So mass, velocity, momentum, energy, those are line bundles. And particular quantities that live in those dimensions, like the particular quantity, the particular velocity of a particular particle at a particular time, that is a quantity that lives in the dimension velocity. And we'll quit here for now. But so that's where we are at the moment. We're learning this concept of dimensional categories, dimensional algebra, dimensional theory. We're learning how it relates to dimensional analysis, and we're learning how dimensional analysis is secretly equivalent to the study of line bundles and sections of line bundles as they occur in algebraic geometry.